Hi guys. Okay, so just that last thought. If we're looking for a component of the energy and not energy itself, often mass cancels and you can reduce down to like GH 1/2 velocity 5L squared. Okay, so just be mindful of that. All right, now another important part of this. You need to be able to qualitatively explain what's happening as well. Give a description of how the energy is changing, okay? And so if we're looking at this example, we have some quantitative numbers, but can we also describe how this is occurring, how this change in energy is happening? My suggestion would be to mark out each of these places. Like I'd call this number 1, 2, 3, 4, and 5, okay? And then I would list out what's happening for each. Like I'd say at number 1, and I'd go and I'd be writing this out. At number 1, we're on the very top of the hill. We don't have any velocity, and so there's height but no velocity, so we have all potential energy, okay? And then number 2, we see a transition from potential energy. We're lowering our potential energy because we're going down the hill, and that's transitioning to kinetic energy because we're gaining a velocity. And so we are decreasing in potential energy but increasing in kinetic. And then at spot 3, I'd say that we have both potential and kinetic energy. We have potential because there is some height still, and as we went down the hill we would have velocity for sure at the base of this jump. And then at spot 4, I would talk about how we still have velocity in the x direction because that's what's giving us an x component to this displacement. And so we see it as well in the y, actually. So both. We have potential energies. We have velocities in the x and y. I guess if we're at the very top of the arc, we could say for just a moment the velocity in the y is 0. But regardless, there is velocity, whether it's in the x direction or the y direction. So there must be kinetic energy then. So we have some kinetic, and we increased our potential because we are at a higher elevation, a greater height than at spot 4. And then that moment right before we hit the ground, all that potential energy transitions to kinetic energy. And so we no longer have a potential, and now it's all kinetic. Okay? So take a moment. I want you to go through and write down and describe what's happening in each of those positions. Okay? And then come back and we'll do example problem number 10. Okay, so hit pause and then go through that and then return to the video when you can. All right, example number 10. How fast is a ball going that is just about to hit the ground after falling off a 50-meter cliff? The ball has a mass of 10 kilograms. Assume gravity and no air resistance. Okay, so we have this 50-meter high cliff, right? And the ball is just going to roll off the edge there, so that's my initial. And then eventually it's going to come, it's going to hit the ground. That'll be the final. Okay? And so whatever energy, the sum of the energy initial has to equal the energy final, and the types of energy we're focusing on are kinetic energy and potential energy. Okay, and so we'll look at what's happening with that initially and finally. Reminder that to have potential energy, we need a height, and to have kinetic energy, we need to have a velocity. At this initial condition, right at that moment that it's about to fall, that we don't have a velocity, so we don't have any initial kinetic, but we are at a height, so we do have potential. And then on the other side of this, my final condition, I don't have a height, so I don't have any potential, but right before it hits the ground, there's quite a bit of velocity, so I would have kinetic. So what I have here is potential energy initial will equal kinetic energy final. And now let's plug in what we know about this. Potential energy is mass, acceleration due to gravity, height. Kinetic energy is 1/2 mass, velocity squared. What are we solving for? How fast is the ball going just before it hits the ground? Okay, so let's rearrange this equation to solve for velocity final. I'm going to divide by 1/2 and mass. Oh, mass is on both sides. Mass can cancel out, right? So we have, now I'll divide by 1/2, which is the same thing as multiplying by 2. Let me write that out. So you could either write this as 2GH or GH divided by 1/2. They're the same, okay? And this situation is going to equal velocity final squared. We want velocity final, not squared, so we're going to take the square root of both sides. So that would leave us with the square root of 2GH equals velocity final. Now, let's make sure we do end with units of meters per second to make sure we rearrange this correctly. So 2 is unitless, g is an acceleration due to gravity, so that would be a meter per second squared. And then we have a height, which is in meters, so that would be meters squared per second squared, and again, it's in a square root, so we do end up with meters per second. Okay, good. So let's plug this in. Square root 2 times by 9.81 times by that height, which was 50. And then it looks like we're working with 3 significant figures, so that'd be 31.3 meters per second. Okay. Example 11 and 12. Okay, 11 I'm going to have you do on your own, but it's really similar to what we talked about with the skier. So let's just set up the situation. Explain the transfer of energy for a motorcyclist jumping over a line of cars. Start with him being at rest, accelerating, jumping, and then landing. So we have this line of cars. Okay, and we're going to have this motorcycle. And it's going to start from rest, it's going to accelerate, it's going to jump, it's going to come back down and land, okay? And so there's multiple different spots here that we can talk about what's happening. We can have this be position 1, 2, 3, and 4. Okay, so I want you to lay out what's happening at 1 as far as energy goes, what's going on at 2, 3, and 4. Okay, write out what you believe is happening. And then if you need a refresher, go back and watch this part of the video where we talk through each of those. Okay, and now example number 12. Jasmine Swanson holds a 1.20 kilogram bob of a pendulum at a level at which the gravitational potential energy is 3 joules, and then releases it. Predict the speed of the bob as it passes through the lowest point of the swing. Where are we at time-wise? Okay, so what we're going to have going on here is, like, if this was, we'll do it this way, this was the pendulum, and that's the bob, that's the mass on the end. She's picking it up, so that has a potential energy of 3 joules, and then she's going to let it go. And you want to know, predict the speed of the bob as it passes through the lowest point of its swing, because it's going to do this, right? Let's draw a picture. Okay, so she's holding it up at some height that allows there to be 3 joules of potential energy, and then releases it. Okay, so that's the initial. There's the final. Okay. Predict the speed of the bob as it passes through the lowest point. Okay, so here's my initial. Here's my final. So whatever energy we start with, we end with. Potential energy initial plus kinetic energy initial will equal potential energy final plus kinetic energy final. Let's see where we're at. Now I chose to make the ground, or my origin, right at the bottom of the swing here, and that was purposeful because I didn't want there to be any height in my final condition here, so that I could say that the potential energy final is 0. And then the other thing that zeroes out here is she releases the ball, and so that means initially, that like moment she releases, we don't have any velocity, so we wouldn't have any initial kinetic energy. So potential energy initial will equal kinetic energy final. We know that the potential energy is 3 joules when released. So this potential energy initial, that's 3 joules. So we don't want to break that into its different parts because we know what it is in its entirety. Kinetic energy, 1/2 mass velocity squared. The question is asking us to predict the speed of the bob as it passes through the lowest point. Well, that would be the velocity, right? So I'm going to rearrange to solve for this velocity, starting by dividing by 1/2 an m. So potential energy equals velocity final squared, and then I'll take the square root of both sides. Okay, so at this point I have all the info. We're just plugging in numbers. Potential energy initial is 3 joules, the mass is 1.20 kilograms. So the square root, top of the fraction, 2 times by the 3 joules divided by 1.2 kilograms. 3 sig figs. So we got a 2.24 meters per second. Now it's a velocity, so we want it to be meters per second. We are taking potential energy, which is joules, dividing it by mass. So we're taking a joule and dividing it by kilograms. A joule is a kilogram meter squared per second squared. And anytime you divide, it's the same as multiplying by the reciprocal. So we're left with meters squared per second squared, but it's all in a square root. So we are left with meters per second. Okay, last thought. We can figure out the efficiency of an object and its useful work or power put in, useful or work or power that is derived, that is given by the object or the machine, versus what we put in for it to produce that. So one way I like to think of this is if I put 100 joules of energy or work into pedaling a bike, that would be my input, and then the bike only gets me to a speed where I have a kinetic energy of 50 joules. Well, so that would be 50 joules is the output, 100 joules is the input, and what we end with is 50% efficiency. My bike is only 50% efficient at taking the energy that's put into it and producing useful energy like kinetic energy, which results in the velocity. Okay, so we don't have this ideal like 100% efficiency, and you won't see that. You also will never see that the output is greater than the input. Okay, well, that is it for this unit.